Okay, we're going to cover Chapter 12, Section D, Projectiles with variable velocity. So an object traveling under the force of gravity alone is called a projectile. So for example, a baseball in flight would be a projectile. So the only acceleration that we've got here going is gravity, which is 9.81 meters per second at the surface of the Earth. So write down in terms of gravity the acceleration vector for a projectile taking the positive y direction up. So if you have a ball that's just thrown straight up in the air, then there's no horizontal component, and so my um, uh, acceleration vector is simply 0 over negative g. Now, the negative is important because gravity is always pointing down, right? So acceleration is always going down, so that's why this has to be negative. If um, if gravity is positive 9.8, then we have to have a negative sign here. Okay, the next question says, at time equals 0, a projectile is launched from speed, just we're calling it u, uh, at an angle of alpha uh, to the horizontal. Find the initial projectile uh, as a column vector in terms of u and alpha. Okay, so my initial vector, um, so let's think of it this way. Um, I'm throwing something in this direction, u. Just the arrow should just be pointing this way, and at an angle alpha. Okay, so we're going to write a column vector. So in our column vectors, um, we have our x value and our y value, right? So and this is u is our velocity. Okay, so so in the x direction, going going left and right. Okay, um, we can think of this as it's touching the angle, right? So that's our adjacent side, and this here is our hypotenuse. So if I'm dealing with adjacent and hypotenuse, I'm going to be using cosine. So I'm going to say cosine of angle alpha is going to be equal to the adjacent over the hypotenuse. So cosine angle alpha is equal to adjacent x over the hypotenuse u. So now I could put this over 1 and cross multiply, or just multiply u on both sides, and I get x is equal to u cosine alpha. That's the direction, that's how far in the horizontal direction I go if I'm going at a speed of u with this angle. Now let's talk about in the up and down direction. In the up and down direction, and I've got this angle, this up and down direction is opposite, and we still have this hypotenuse here. So if I've got opposite and hypotenuse, I'm going to be using sine. So I can rewrite this. Um, so if I'm going, uh, if I've got opposite and hypotenuse, I'm going to write sine. Sine of alpha equals the y movement, the up and down movement, over the hypotenuse. And now I can rewrite this in terms with y equals u sine alpha. So if my left and right direction is u cosine alpha, and my up and down direction is u sine alpha, my initial velocity is going to be u cosine alpha, u sine alpha. I'm going to be referencing this again and again. So at time equals 0, this is my velocity vector. Okay, next question. Okay, I guess that was question 2. Okay, next question. Use integration to find the velocity vector for a projectile at time t. Okay, so if I'm going to use integration, we start off with acceleration. Okay, so we know acceleration is, from our part A, is 0 if it goes left and right, not at all, and it's pointing. The only thing we've got going is it's pointing down. Acceleration is pointing down. and that's gravity. So if I'm going to write this as a velocity vector, I can take the antiderivative of 0 dt and the antiderivative of negative g dt. Okay, and so the antiderivative of 0 gets me um, some constant. I'm going to call this constant u subscript 1. And the antiderivative of negative g is going to give me negative g times t plus u subscript 2. So they use this in the book, so I'm using the same u. So we're letting u1 and u2 be constants of integration, just like we use the letter c be the constant of integration. Okay, so now I can say, okay, so when time equals 0, we know our velocity is this up here, right? U cosine alpha, u sine alpha. So that means u1 is going to be u cosine alpha, and u2 is going to be u sine alpha. So so I can rewrite this since I know I'm going to replace u subscript 1 with u cosine alpha, and I'm going to replace u subscript 2 with u sine alpha. So this is my velocity vector over time. Okay. You may want to rewind and to see that again if you need it. Okay. Next page. Okay. At time equals 0, the particle has displacement c subscript 1 and c subscript 2. Find an expression for the particle's displacement at time t, the particle's projectile from point 0, 0 on the ground. Okay, so the first thing I'm going to do, so displacement, we're going to use the letter r for displacement. I don't know why they use r, but that's what they do. They don't use the letter d. Okay, and x and y is the x location and y location. So we have to do the antiderivative of our velocity vector. Okay, on the previous page, we found the velocity vector was u cosine alpha, and then in the x component, and the y component is negative g times t plus u sine alpha. Okay, so I'm going to take the antiderivative of these, and if I take the antiderivative of those, then the antiderivative of u cosine alpha is going to be u cosine alpha t, and then plus c subscript 1, and then the antiderivative of negative gt is going to give me the power of t becomes 2 squared, and then so I'm going to have to put a 1/2 in front. Okay, and then the antiderivative of u sine alpha becomes u sine alpha t, and then we have to put plus c. That's our constant for in the y direction. So so at time 0, we've got c1, c2. Now, since the particle starts at 0, 0, we would have c1 equals 0 and c2 equals 0. So this could be simplified to this when c1 is 0 and when c2 is 0. Okay, this is going to change because I mean in this particular case we're starting on the ground, and we're starting at the origin. Okay, there's going to be times when we're starting at like on a cliff and we're raised up or something like that on some later examples. Okay, question 5. Use your answer from question 3 to find the time at which the particle reaches the maximum height. Okay, so from question 3, it's going to reach the maximum height when the velocity is 0. Okay, that should make sense, right? If I'm going up, I've got a positive velocity, and then I get to the top, and then I start going down. My velocity changes again. So the velocity is when I reach the maximum, when I've thrown something up. Okay, so here's my velocity vector from the previous page. And if the velocity is 0, I'm going to make my y component equal to 0. The x component doesn't affect when I'm at a maximum height. The only thing affecting height is the y component. So when the velocity is 0, the y component is going to have to be 0. Okay, so now I've made gt plus u sine alpha, I've made that equal to 0. Okay, so now I can add gravity time. I can add that on both sides of the equation, and we're solving for time, right? Find the time. So I'm going to divide both sides by g, and then we get this. So this is the time when the particle reaches the maximum height. I'm going to be coming back to this formula throughout this assignment. So you're going to see me coming back to this over and over. Okay? And we're going to come back to some of the earlier formulas as well. Okay, use your answer from question 4 to find an expression for this height. Okay, so an expression for this height, what did we do? So we're going to start off with this. Now this is the formula that I came up with here when we started at 0, 0. That when I started at 0, 0, our C1 value was 0 and our C2 value was 0. So we're starting off with this displacement vector. Okay, and we want to use this to find an expression for this height. So this height, we're going to reuse this here, and so the height is 1/2 g parentheses t squared plus u sine alpha times t. Now we know we've reached the maximum height at this time, right? So when time is equal to this, then I'm going to substitute t with u sine alpha over gravity. Okay, and so when I substitute that in, the pink dot t is now going to become this. So don't be afraid of this equation. I've just rewritten this line right here that I'm pointing at. I've just rewritten this line down here, and I've replaced the letter t with u sine alpha over gravity, and I replaced this t with the same thing. Okay, so now we can simplify this a little bit. So I can rewrite this as, because I've got u squared, I've got sine alpha squared, and I've got gravity in the denominator squared. So I've simplified that. And then this, I just wrote it as a single fraction. I've got sine alpha times sine alpha gives me sine alpha squared. I've got u times u, that gets me u squared. Okay. So I've got gravity in the numerator, gravity squared in the denominator. That can simplify to just a single gravity. So now I look at this term and this term, and we see, oh my gosh, I've got u squared sine alpha squared over gravity here, and I've got that here. So negative 1/2 of the green stuff plus the green stuff is going to simply simplify to y equals 1/2 of this stuff squared over gravity. Okay, so this is the expression for the height of a particle when we reach the maximum height. Okay, we're going to be coming back to both of these formulas quite a bit when we start doing the problem numbers. Right now we're just deriving the formulas, okay, to see where they come from. You're not going to need to memorize the formulas on the IB test. But right now we're just using them. Okay, so question 7 says, if the initial speed of the particle is fixed, what is the value of alpha? Which value of alpha will result in the particle's maximum height reached? Okay, so so the maximum height reached is when alpha is 90 degrees, and this should just make perfect sense, right? Because that means if the angle, if the projectile is thrown straight up in the air, then then that should reach the maximum height. So, because alpha sine alpha theta is going to be the largest value when we're at 90 degrees, and you can see that on my unit circle, right? The sine is going to be highest at 90 degrees. Okay. Never thought you would be using this unit circle as much as we have all year long. Okay. Let's move forward. Question number 8. Use your answer to question 4 to find the time at which the particle hits the ground. Okay, so we need to think about this for a second. When the particle hits the ground, the y value is going to be 0. So using the formula that we had for the y from the y vector, this thing here. Okay, we can go back to that formula. Okay, here is the vector for position over time, and the y value tells us our height. I've highlighted it here in yellow. Okay, so so we're going to make this y value, the height, we're going to make that equal to 0 because we want to find out when it hits the ground. Okay, so if I've made this equal to 0, both terms have a t. I can factor the t out, and so so this is going to be equal when t equals 0, and it's going to be equal to 0 when this here is equal to 0. So this here is what I'm going to focus on. I'm going to make this equal to 0 so I can add 1/2 gt on both sides, and we want to find out the time when the particle is 0, right? Time. So to find time, I'm going to divide both sides by gravity and multiply both sides by 2. And then I get this. Now, this should look familiar because we just calculated what time to get to the maximum. And you're going to notice that this is twice our answer from the earlier part. Notice it's 2u sine alpha over gravity. And over here, we found that it was u sine alpha over gravity. And this is the time to reach the maximum, right? So the time to reach the ground again is going to be multiplied by 2. So it's on the ground. The time it takes to reach the ground is going to be this. Okay, so you might want to hit pause if you want to copy this down. Okay, so let's look at the next one. I guess this is question 9, huh? Okay, so the range of the particle is the total horizontal distance traveled when it returns to the same. Okay, the range of the particle is the total horizontal distance traveled until it returns to the same height at which it began. So when it's back on the ground. So find the expression for the range of this particle. Okay, so the range is the horizontal distance, the x value of my vector. Okay, so the horizontal distance of my of displacement for my vector, if I go back to here, the horizontal distance is u cosine alpha t, right? So the horizontal distance is u cosine alpha t, right? And um, so the total horizontal distance it goes and is using this, and now we're going to substitute t, the value that we just got here, because at this point it's back on the ground, it's not moving anymore. So this is the time it takes to get back to the ground again. So I'm going to replace time with the 2u sine alpha over g. Okay. And now I've replaced t with this, and we're trying to find an expression of the range for this particle. So now we've got this expression, and we can simplify it. I've got u and u, I've got u squared, I've got 2, I've got sine alpha, I've got cosine alpha, and I've got it all over g. So this is the total horizontal distance traveled. We're going to be using this formula as well. We're deriving all of these formulas, and we're going to be coming back to these pages to look at it. Okay. If the initial speed of the particle is fixed, which value of alpha gives the maximum range? Okay. So the maximum range or x value that we're going to get is when this sine alpha cosine alpha is biggest, right? Because the two, the u and the g, aren't going to be changing. So if I want to find the maximum range, the maximum our projectile goes over, if it's too shallow, it's not going to go far, and if it's too straight up, it's not going to go far. So we need to figure out what is our maximum range. So we need to find out when sine alpha cosine alpha is going to get us our biggest number. Okay, so on my graphing display calculator, I can type this in. I'll do it right here with you. Okay. And I'm going to type in sine x cosine x. Okay, make sure your mode is in degree mode, and your function mode needs to go back to here. We're not doing, we're not in sequence mode anymore like we were for chapter 11. Okay, so I'm in function mode. Okay, second quit. Okay, so I've hit y equals, and I'm here, and I need to change my window. I'm going to change the x max to 360 because we're dealing with degrees. And I'm going to change the y min to -1, and I'm going to change the y max to 1. Okay, because sine alpha times cosine alpha is not going to be greater than 1. Okay, so now I'm going to hit the graph. Okay, so the maximum range is going to happen when this is at its maximum. So to figure out this maximum, I can press graph, and we get this picture. And then if I do second trace, I'm going to find the maximum. I'm going to go down to 4, maximum. And now I have to do left bound. So notice it's right here. I need to get over here, right? So I'm going to hit the left arrow. And I hit enter. Now it says right bound. I'm going to go over to the right side of the hill. I hit enter. It says guess. I hit enter. And my maximum happens at 49.99999. Let's just call that 45 degrees. Okay. So when alpha is 45 degrees, it's going to shoot us the furthest out to the right. Remember, hit pause at any time if you need to. Okay. All right. Now we're going to use all those formulas which we just derived. A ball is projectiled from the ground with initial speed of 15 at an angle of 30 degrees, and the acceleration due to gravity is 9.81. Find the horizontal distance traveled by the ball before it hits the ground. Okay, so the horizontal distance we just figured out on the previous page was this. You could flip the page over to see that this is what we calculated for the horizontal distance. See? Right there. Ah. Okay. So, I'm going to replace u, because that is our speed of 15. Our angle we know is 30. And for gravity, we're using 9.81. We plug this into our calculator, we get this. Okay. Question 12. Find the maximum height of the ball. So if you go back to the earlier page, you're going to find the maximum height is given with this formula. So once again, we know that our speed, u, is equal to 15. Alpha is equal to 30. Now, we need to make sure, if you're, in order to prevent yourself from making a mistake, you might want to put the parentheses here for the 2G. Otherwise, you're going to make a PEMDAS error. Okay, and then, in a more realistic model, what additional force do we need to worry about in predicting the flight of a ball? And so, what we need to worry about is air resistance. But for this course, we're just going to neglect air resistance and not do our calculations worrying about that sort of thing. Okay, so factual. What does a column vector describe in a projectile motion? Okay, so vectors can be used to describe projectile motion, the horizontal distance, and the vertical component. Okay. That's why we're using the column vector, to distinguish the left and right motion and the up and down motion. Okay, and then question 15, and then the rest of it I'll make in a separate video. How are vectors useful in describing projectile motions, and how do we find the velocity equation? So vectors can describe angular velocity in circular motion by using derivatives and displacement.